So this is the last lesson in a difficult unit on trigonometry, and while the notes aren't terribly long, this is perhaps not surprisingly going to be a fairly challenging lesson, and that what we're doing, again, as we've done at the end of every chapter, is returning to the idea of looking at how to solve trigonometric equations. This time, identities will come into play, and every single chapter in this unit has come back to this idea, so it's definitely an important part. This some of these equations expect to be quite challenging because it really draws upon our knowledge of the entire unit in many ways. All right, but at some point, identities will come into play. That's it. I want to solve a trigonometric equation. Notice I have one here. My restriction is quite simple, from 0 to 2 pi, so that won't be the big deal. The question is, how do I solve this? Notice right now I have cosine functions on both sides, but one has a 2x as its input, one has an x. So they're not like terms. I can't bring them to the same side and take out a factor of cos x because they don't have a factor of cos x in common. One has 2x going inside it, one has a single x. So what I can do, though, is cos of 2x, hopefully it looks familiar. That's your double angle identity for cosine. And I have 3 choices. So that I've expected us to memorize. Of the 3, if I choose this one, 2 cos squared x take away 1, I think that's the most useful because I can just see that that minus 1 I just wrote down and the plus 1 I had in my equation are going to cancel each other out. And that's why I'm choosing it. If you just pick one at random, you can still get this correct, but it'll probably take a bit more work. And in general, if you can kind of see ahead, if you have a reason for choosing one of those, that definitely helps. That's it. Like I commented on, these cancel out. So I have 2 cos squared x equals the cosine of x. Now this should look familiar. We've done stuff like this before. Doesn't mean it's easy, but I'm hoping it looks familiar. We want to now, we have cosine functions on both sides. Yes, one is squared, but they both have just x as an input. So now let's bring them to the same side. Essentially, this is a quadratic and trigonometric equation. So we'll subtract cos x from both sides. And take out a factor. Now I can take out a factor of cosine of x. And now I can expect my 2 factors. And so if I look at this, I have to think about where does cos of x equal 0? And if I look right here, I have to think about where does cos of x equal 1/2? All right, so all of these relate back to special angles where cos equals 0 or cos equals 1/2. So we shouldn't need a calculator here at any given point. And so where does cosine equal 0? Well, cosine, if I just go back to this quickly, cosine starts at 1, goes down to 0, goes all the way down to -1, back up to 0, round and around. So cosine equals 0 anytime we have an angle coterminal here and here. And my restriction was from 0 to 2 pi, so that's only at pi over 2 and 3 pi over 2. Oops. Okay, and where does cosine equal 1/2? Well, again, let me visualize my angle in standard position. Again, we kind of keep coming back to this idea as we're solving equations. I'm trying to find out where cosine is positive. And so cosine is positive in this quadrant and this quadrant. Now, where does cosine equal 1/2? That's when the reference angle is 60 degrees or pi over 3. So I know this reference angle is pi over 3. And so now, again, thinking about my restriction, I can see my 2 angles must be pi over 3 and 5 pi over 3. Clearly, if my restrictions were different, that would affect my answers. That said, most of the questions I'm going to look at, I'm going to give pretty standard restrictions because, again, that part is nothing new. Not saying it's easy, but those are all my solutions right there, 4 solutions. Okay, relatively quick in some ways. It definitely helped that this came back to my special angles. But again, at some point, I needed to utilize that one identity. That's the only thing that really made this new. But please don't think that means I'm saying it's easy. Okay, let's look at this. So again, I want to solve this. I got a lot of stuff going on. I have no restriction, so that means I want to find the general solution. But again, I'll get to that last. So first, cotangent. Let's rewrite cotangent in terms of sine and cos. And so cotangent is the same as cos over sine. So cos x over sine x. And now, hopefully we can see these sine functions cancel out. So I can now simplify this down to just cos squared x equals cos x. Well, that's mighty similar to what we were just doing. So again, I have this quadratic expression that has trigonometric. Essentially, it's a quadratic function or quadratic equation with a trigonometric equation inside it. So I want to subtract cos x from both sides so I can factor this. So take out a factor of cos x. And now again, inspect my factors. So here I have to think about where does cos x equal 0. Well, I've already talked about that, but I'll get to that in a second. And here I need to think about where cos x equals 1. I've informally already spoken about that. First, cos x equals 0. We saw the exact same thing in the last question. We saw cos x equals 0 at pi over 2, 3 pi over 2. The next would be 5 pi over 2, and so on. Again, I want all the solutions. I want the general solution. So where does cos x equal 1? Cos x equals 1. In fact, maybe I'll just go back up here. Right. If I look right here, I mentioned that cosine starts at 1. And then it will reach 1 again when we get to 2 pi, and 4 pi, and 6 pi, and so on. And so if I look right here, I can say here that x will equal 1 at 0, and 2 pi, and 4 pi, and so on. Okay, but I got to be careful, because if I look right up here, yes, I canceled out sine, but still, if I look right here, I have a denominator of sine. And so I also have to check to make sure that sine x never equals 0. If sine x ever equals 0, then I'm dividing by 0 right there. Or another way of looking at it, when any of the places where sine x equals 0, cotangent is undefined. So where does sine x equal 0? Sine x equals 0 at 0, and pi, and 2 pi, and 3 pi, and so on. Which, notice, all of those values, or I should say all of these values right here, are part of this list. And so I need to reject these. Again, anytime x equals 0 or 2 pi or 4 pi, that cotangent function, when I substitute x with that value, will not be actually evaluated. And so all of those have to be rejected, which means my solution is only these ones right here. And so let me now just think about how I can express all those values as an algebraic statement. So I'll say, therefore, x equals, I'll just pick one, pi over 2 plus, from here to here, how far is it? It's always, I'm adding pi every time. So plus any multiple of pi, or n belongs to the integers. So not a lot of algebraic work, but a pretty tricky question. I think mostly because for one of the first times when we're in this unit, when we're solving equations, we have to think about restrictions. And we saw that in other parts, especially with rational equations, but not so much in this course. Actually, would have dealt with that in grade 11 perhaps, and we'll see it again going forwards. However, earlier on in this unit, we did have to deal with finding restrictions on expressions, and so hopefully the idea of understanding why sine x can't equal 0 right here is not new, because that went back to the first part of this chapter, but never applying it with an equation. Or another way of looking at it, if x really could equal 0, if that really was a solution, well, how could that be a solution? Because if I put a 0 into x right there, this cotangent function is undefined. So how on earth can we say x is a solution to this equation if you can't even put it into all the expressions? Right? Either way, let's move on. Let's look at this. Okay, so again, no restriction. So in the end, I want the general solution. But again, that's not the main part. All right, so I got sine and cosecant. Well, good thing is cosecant is the reciprocal of sine. So I'm going to rewrite this as 2 times the sine of x equals 7 minus 3 times 1 over sine x. Or, instead of writing it like that, instead of writing it as 3 times 1 over sine x, why don't I just write it as 3 over sine x? Right, 3 times the cosecant of x is the same as 3 divided by the sine of x. Okay, so at least now I have the sine function as my only type of function here. So what can I do next? Well, we always have choices. I would recommend canceling out that denominator of sine x, which is really quite easy to do if I just multiply everything by sine x. Just gotta make sure I multiply everything by sine x. So if I do that, I have 2 sine squared x on the left-hand side. On the right-hand side, I have 7 times the sine of x minus 3. So sine x cancel out. However, let's make a little note right here that sine x cannot equal 0. Okay, I'm going to make that note right away so that if it does come into play later on, I don't forget about it. That's it. How do I solve this? Well, now I have the makings of a quadratic equation again. So let's bring everything to one side and make it equal 0 and factor this. And again, factoring this is the same as factoring 2x squared minus 7x plus 3. Should take a couple of steps. But the factors of this, you should end up with sine x minus 3 for one factor and 2 sine x minus 1 for the other. And again, this all equals 0. All right, now let's inspect my factors. Now, and again, as I always want to say, I did this in one step because I already had it written down. I don't expect you to be able to factor by looking at it. It takes a couple of steps, but it shouldn't take long. That's it. Let's look at this. Here I have to think about, where does sine x equal 3? Well, sine x will never equal 3, right? The biggest value that can ever come out of a sine function or a cosine function is 1. So that means there's nothing more for me to do. That factor doesn't lead to any solutions. That's nice. Let's just look at this now. Here I have to think about, where does sine x equal 1/2? Well, that's definitely going to be possible. That leads to a special angle. Hopefully we can do this quite quickly. Again, sine is positive in the first and second quadrants, and the reference angle is wherever sine equals 1/2, which is 30 degrees, or pi over 6. And so, these are my first two positive solutions, but I want the general solution. So all in all, I can say, therefore, x equals pi over 6 plus any multiple of 2 pi and 5 pi over 6 plus any multiple of 2 pi. And so again, notice, and actually before I go on, let me just go back and look at my little note I made right here. I said sine x can't equal 0. But that's okay, that doesn't come into play that doesn't affect any of my solutions. Remember, sine x equals 0 at 0, pi, 2 pi, 3 pi, and so on. None of those are my solutions, so I'm okay. But notice again, it connects to all parts of the unit, especially going back to the end of chapter 4, which I kept saying was such an important part. So this final problem, the final problem of this unit, not surprisingly, is going to be a little bit mean. But again, it won't involve a ton of algebraic steps, but this is a tough question. Okay, so how do we solve this? Well, first, we always have choices. But one thing I notice is I have secant, I have sine of 2x and secant of 2x, so it's both the same input. But I have, I don't like secant. No offense to secant. But I want to rewrite secant as 1 over cosine. Well, having 1 over cosine in the denominator is the same as having cosine in the numerator. So everything I see here, I can rewrite as 8 times the sine of 2x times the cosine of 2x equals 1. Dividing by secant, same as multiplying by cosine. Okay, next, what I see here is similar to the form of my double angle identity for sine, except my double angle identity for sine, which I'll write over here, the sine of 2 theta equals 2 times the sine of theta times the cos of theta. I have similar in form. I can make it even closer if I take out a factor of -4, and then I have 2 times the sine of 2x times the cosine of 2x equals 1. So if I look right here, essentially what I have, actually I'll pick a different color. What I have highlighted in yellow is the same form as what I've highlighted in yellow right there. So now I want to take this and put it into this form. And so I'm going to rewrite this equation as still -4 bracket, but instead of 2 times the sine of 2x cos of 2x, I want to have it written in this form. It's just the sine of 2 times the input. So in this case, it's going to be the sine of 2 times 2x. And again, if you look right here, the input, my input of each of those functions has to be the same. It's 2x, just like I have a theta over here. And so now I double it from theta to 2 theta, from 2x to 4x, it's going to equal. Okay, that's it. Well, I think one of the hardest steps done. So I now have minus 4 times the sine of 4x equals 1. All right. So what can I do next? Well, let's divide both sides by negative 4 and isolate my sine function. The sine of 4x equals negative 1/4. Okay, now, this now connects back to the end of chapter 5 because I have this 4 right here. Now, what does that 4 tell me? If that 4 wasn't there, this question's still challenging, but not as challenging. And so let's make a little note. That 4 affects the period of this function. The period of the sine 4x is going to be 2 pi divided by 4, or just pi over 2. That's going to come into play in a bit, especially since I want the general solution. This wave repeats every pi over 2, not every 2 pi. That said, as long as I don't forget about it entirely, I'm going to ignore the 4x, or the 4 in front of the 4x, and realize, okay, where does sine equal negative 1/4? Well, first of all, sine equals a negative in quadrants 3 and 4. But this is not a special angle. I never asked you to memorize where sine equals a quarter. So I know that sine is negative in these 2 quadrants. I don't know the reference angle. The reference angle, really, I don't really care about the negative anymore. I just care about the 1/4. So where does sine equal 1/4? Again, I never asked us to memorize that, so I want to use my calculator. And so I want to use the inverse sine of 1/4. And so I'm going to type this into my calculator. I'm going to put just a positive 1/4 in, because again, if I put the negative in, it's not wrong, but there's a good chance I will confuse myself. The negative in front of the 1/4 is important. It tells me the quadrants of my solutions. I know those. I can see it. All I care now is what's the reference angle. So if I have my calculator in radians and I go inverse sine of 1/4, I get about 0.25. It's an irrational number. It's actually 0.25268, blah, blah, blah. So it's about that. And that's my reference angle. So I now know each of these reference angles is about 0.25. And now I can start to solve for my solutions. I have one solution here and one solution here in one period. Okay? And so what are those? Well, the first one is pi plus 0.25. And again, these are approximations. Put a little dot over my equal sign. The second one I showed is 2 pi minus 0.25. Okay? Now this keeps going on and on and on, so I'll put a little dot, dot, dot there. However, what goes right here? Not x, but 4x. So what I want to do now is I want to solve for x, not 4x, which is not a big deal. I want to divide everything by 4. Now again, I can use a calculator. So if I divide everything by 4, I get x approximately equals pi plus 0.25 divided by 4 is about 0.85. Again, these are all rounded because those reference angles are decimal approximations. My second solution, 2 pi minus 0.25 divided by 4, is about 1.51. And then I'm going to put a comma, dot, 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 because this keeps going. So now, those are my first 2 positive solutions. All that's left is I want my general solution. Again, if you look at the equation, there's no restriction. So let's think about how would I find the next solution right here? Well, I'd have to add the period. And right here, I'd have to add the period. And now, what was the period again? Not 2 pi. The period is pi over 2. So I want to add pi over 2 or subtract pi over 2 from these 2 solutions any number of times. And so at this point, I can now write my answer. I can say, therefore, x equals, or sorry, approximately equals 0.85 plus any multiple of pi over 2, as well as 1.51 plus any multiple of pi over 2, where n belongs to the integers. So let's think about what this question required. This question required us to first understand some identities, and be able to use especially the identity of cos 2x, of sine 2x in some way. In reverse, we have to be able to understand our special angles. In this case, realize we couldn't use our special angles. We have to remember our CAS tool. We have to remember how that 4 affects the period. We have to remember how to find a general solution. It connects to so much of this unit. This is a tough question. So do not be concerned if you find this tough. But if you want to, at some point, demonstrate, if you feel like you have a really, really strong, proficient understanding of all aspects of this unit, you should be able to get a question like this correct with time. Okay, with time. You know, it takes time to kind of ponder and think, try different things. But this is a tough question. And that's how we've ended the unit. So no more trigonometry videos from me. Goodbye.